Chemical Engineering, Polymer Science 757, Polymer Rheology, Professor H.H. Winter, lecture number 6A. The hard work is done now. Now we can look at polymeric materials in various experiments and use the tools which we developed, use the strain which we defined, use the stress which we defined. Today, I would like to talk about material functions, the material behavior in some well-defined flows, well-defined shear flows and well-defined extensional flows. And this is chapter 3 of the lectures. A whole chapter in Bird, Armstrong, and Hassager is devoted to material functions. And material functions we would define as the stress response to a well-defined strain, say in a rheometer, or vice versa, the strain response to a well-defined stress. But in all cases, it will be a simple experiment, and the analysis of that experiment will be also in a very simple, straightforward manner. The stress in those simple flows is reduced into component form by choosing a specific coordinate system. Now, in shear flow, the coordinate system is giving us a tensor which has a diagonal, 3 components, and has a shear component outside. So the stress has 4 independent components, and it has zeros here, which means that the stress is really given as a plane stress. Remember, this will be one of the principal axes around which we are rotating to get the different components, and those are the interesting components. Now, when generating shear flow in specific geometries, we have one parameter. That parameter is the shear rate. The shear rate determines the shear stress. It determines the first normal stress difference and the second normal stress difference. Remember, we are not able to determine the absolute value of either one of those terms. We need the boundary condition in a flow to find out what the pressure level is. So that would come in addition. For our material function, we only get the first normal stress difference between those two, tau 11 minus tau 22, and the second normal stress difference between tau 22 and tau 33, and that's down here. And to define now the behavior in shear flow, we need 3 material functions. We need the viscosity. That's well known. The viscosity is just the shear stress divided by the shear rate, and that's the conventional definition. But we also need the coefficient of the first normal stress difference and the coefficient of the second normal stress difference. Actually, this should be a 2 here. This is the second normal stress coefficient. And each of those coefficients depends on the square of the shear rate. It doesn't matter whether we are shearing forward or backward. The sign has no influence on that. So we have to discuss those functions in shear flow. We also have to discuss it in extensional flow, where the stress in a suitable coordinate system can be represented in diagonal form. In arbitrary extensional flows, you have 3 extension rates. They are coupled by conservation of mass, so you still have 2 independent extension rates to define the kinematics of extensional flow. Special cases are uniaxial extension, where you just stretch in one direction, and conservation of mass defines the other stretching rates. So there's just one parameter again for uniaxial extension, this extension rate. And the only parameter which is of interest is the only material function of interest is the first normal stress difference. The second normal stress difference is 0 due to symmetry in uniaxial extension, because the stress in 2 direction is equal to the stress in 3 direction, or the stress on a 2 surface is equal to the stress on a 3 surface. In a planar extension, where you stretch your material element in one direction, compress it in the second, while keeping the third constant, this third dimension constant, you would have two normal stress differences which are different from each other. Again, there would be just one extension rate, which is that of the planar extension, but there would be two material functions defining the flow. Note that in extensional flow, you can have an infinite number of different types of extensional flows depending on the definition of your extension rates. While in shear flow, you only have one parameter, that's the shear rate. That's why from all the possibilities in extensional flow, I just picked the uniaxial extension and planar extension. And I will go through an example for uniaxial extension in a moment. But let's stay with shear flow in the moment. Let's define shear flow in terms of a coordinate system and in terms of material planes moving past each other. Actually, we have a little sketch here of those material planes. Shear flow is defined as a flow where material planes move past each other rigidly. Here I put in some discrete material layers. In reality, that's a continuum which is moving past. But I just want to demonstrate that there are layers which move past each other without deforming. So if you have 2 points in one of those layers, they will maintain their distance, and angles within that plane will also be maintained. There's no deformation. It's a rigidly moving material surface. The shearing is seen as a gradient in direction normal to that surface. So you could, for instance, mount a pencil on one of the planes and draw a line on a neighboring plane below, and that line now would be called a so-called shear line. And the direction of that line is the shear direction. You can do that in a circumferential flow, in all kinds of flow geometries. You can do that for defining one direction of your coordinate system, because the direction of that shear line will be our one coordinate. This is chosen here. This is x1, and 2 is the direction of the gradient. It's normal to the shearing planes. And 3 is the vorticity direction. It's a neutral direction for our stress tensor, or it's the third principal axis of the stress. If this direction now of shearing stays constant over time, then we call the flow a unidirectional shear flow. If the flow changes direction, let's say it goes for a while in this direction, and then it goes in maybe in the other direction here, in the 3 direction, then we would change our direction, and we would introduce a transient behavior in shear flow. Even at constant rate, we could do that experiment. By maintaining our shear rate, we would maintain our velocity gradient in 2 direction, but we would change the shear direction, and there would be a transient behavior as a response to that. Therefore, for steady shear flow, which we will define later on, we will require a constant shear rate in time, and secondly, we will also require a constant shear direction that cannot be altered in that experiment. That will be then for steady shear and for discussing material functions in steady shear. The coordinate system is listed again here. This is our simple coordinate system which we discussed. And the rate of deformation tensor reduces to diagonal form. Here it has just the shear rate in the off diagonal, and I just put 2 times d because of the definition of the rate of deformation tensor. So this is the instantaneous rate of deformation of the material in shear flow. There are many, many applications to shear flow. I listed a few of them. You could look at pipe flow, flow in an annulus, coed flow, helical flow, flow in a sandwich geometry. Yeah, I drew a few of those geometries. When you take a plane slit, for instance, and have one surface stationary, the other one moving, then just due to the relative motion, there's a velocity gradient normal to that surface, and you introduce a shearing motion. And if the gap is constant in flow direction, then you're generating shear flow. Same flow could be generated in an annulus where the center is moving, it's just dragging the fluid along. A geometry like this is produced in wire coating, for instance. Imagine you want to put a plastic coat on a metal wire. And you would drag the metal wire through a housing which is fed from one side with polymeric material, and then it comes out coated, and you cool it and use it. It might not be just drag flow in wire coating. You might have some pressure on the upstream side, so the flow might also be due to high pressure, and then you would have a superposition. I drew something like this here, superposition of drag flow and pressure flow in this geometry. Shear flow might also be generated by pressure flow in a pipe or in a slit. Here, pipe, you have axisymmetric. That's why I put the coordinate system in the center. Here, it's a slit which has stationary walls, and the flow is just due to a pressure gradient. Again, all of those flows are described by the same material properties, the material properties of shear flow. So if we measure the behavior in one shear geometry, then we can use that measured material function, it's called the shear viscosity, to model and to predict shear flows in all those geometries. And that's what's been done in polymer processing, for instance. So we will discuss a little more time on the shear behavior. I will go into further detail because of the importance of shear flow. The strain we discussed, the strain components of shear flow, we discussed already. You have all the tables describing the strain. This is the velocity field, the deformation gradient, and yes, the deformation gradient here. This is the velocity gradient, deformation gradient, and the Cauchy, the finger strain tensor. And these components are used for any of these shear flows. Right? That's the point I wanted to bring across. And there was, when we discussed that, there was this question, can you use this for a flow between parallel plates where the material element goes on a circular streamline, or as compared to flow in a pipe where material element goes at a constant radial position but goes down the pipe in axis direction of this pipe. And the answer is yes, it's always reduced to the same strain components. So that's one type of flows we will be looking at when we talk about material functions. The second type of flow is extensional flow, where a material element, like a little cube here, while it's moving along, is stretched. And the definition of that type of flow is given as the vorticity being equal to 0, or nabla across the velocity vector, or the velocity can be described as a simple scalar field, which is nice, for instance, for thermodynamic analysis of flow behavior. Experiments to look at this behavior would be stagnation flow or sink flow, or just stretching of a rod. If you have a material which is viscous enough so that you can grab it and stretch it, then that would be the way to generate the extensional flow. The stress components are here the diagonal, and we would like to look at those under different conditions. We would like to measure those, and again we would use the table which we generated for the velocity gradient, deformation gradient, and the Cauchy and the finger strain tensor, nothing specific. One material function which has been studied extensively, material function in extensional flow, is the stress response to uniaxial extension, stretching in one direction and symmetry in between 2 and 3 direction, like stretching of a fiber, stretching of a rod. And I want to go through that as an example now with you so that you can see the details. The velocity field is given by one parameter, the extension rate. And away from a stagnation point, then the velocity is just given by the distance x from the stagnation point times this extension rate. The stretching in r direction is given by this here, or the stretching in the second direction is given by this. And due to the coordinate system, choice of coordinate system, there's a 0 in 3. So you have to watch out when writing the components now in a cylindrical coordinate system. It's a curved coordinate system, and this is the kinematics. Those are the components in that curved coordinate system. The velocity gradient now in curvature is, the divergence of the velocity is given as such, and this is equal to 0 at constant density. The rate of deformation tensor has those components, and you can see it's given by the extension rate, and the 2 and 3 component then is, as expected due to symmetry, is compensating for the stretching in one direction. Geometrically, you could picture that flow as the stretching of a little cylinder, which is in the beginning very short, and then as time goes on, the cylinder gets longer and longer. Try to sketch this cylinder here. This is just a side view of a cylinder. It's not a square. It's assumed to be with rotational symmetry. And then the cylinder is being stretched, so at some later time it is of smaller radius but longer, and it's getting even longer. Due to conservation of mass, we know where the corner point of the cylinder is. It follows just a hyperbola given by x r squared equal to constant. So this is the motion of this point, this corner point of the cylinder. In fact, every internal point of the cylinder is moving along a line like this also. Just the value of the constant is getting smaller and smaller as you move closer to the center. So basically, the flow which you're generating when stretching a cylinder like this is a stagnation flow. The velocity here is 0, and it increases linearly with the distance from the center of that flow. It's a flow where we kind of fixated with the free surface. We are looking at the outer geometry of that cylinder, but we could look at any interior point of that extensional flow, and then we would see that it's really moving on a velocity field as described here, or as I sketched, if you remember here, if I sketched it in our outline for all the tables of deformation gradients here. This is the type of stagnation flow which we are generating. And again, we can use the same details, the same analysis to describe the flow of our fiber. Note that a plane surface, see the head here, this would be circumferential, this would be the head of this little cylinder, is plane here, and it will stay plane at all times. That means that a material plane like this moves at a constant x velocity. It's translating at a constant x velocity. And you can see that in the kinematics. Let me pull up the initial kinematics. You can see that the velocity in x direction is just a function of x. It is independent of y direction. So a plane surface like this, plane surface normal to R, will always be plane at all times. And also a surface normal to the, wait a minute, this is the x direction, of course, and this is the radial direction, sorry. And so, and now a surface normal to the radial direction here is a material surface, and it always will move together and will not be distorted. That's why the cylinder remains a cylinder while we are stretching it. So this is inherent to the kinematics of extensional flow, and it's consistent with the previous picture. We can calculate now the change of the length of this rod in terms of the kinematics. This is the rate of change of the length. It's given by the instantaneous extension rate multiplied with the instantaneous length. Or you could say the extension rate is given as the rate of change divided by the instantaneous length. And integration gives us the length change. Now here I allowed the extension rate to be variable with time, so you can just integrate to get the total stretch. From the total stretch, together with conservation of mass, now you get the instantaneous radius. This is the radius at 2 times, and it's just given by looking at the volume times the density at 2 times. So this describes the shrinking in radial direction for conservation of mass. In the case of constant extension rate, this integral reduces to just an exponential function. This will be a constant times time. So the length at some time t is equal to the initial length times the exponential function, like this. So with time, this length increases exponentially. If you would hold on to this end, excuse me. If you hold on to this end here in a stretching experiment, then and pull the fiber, then you have to pull faster and faster in an exponential fashion to be able to maintain a constant extension rate, because your instantaneous rate of stretching is always divided by the instantaneous length of that element. And now comes a trick which was used to measure extensional viscosities at times where one didn't have drives like this. Now you could buy a drive very easily which pulls in this exponential fashion. That would be very easy to do. But 10 or 15 years back, it was impossible to do that, simply to have this type of type function in a drive. And for overcoming the problem, Meissner in Germany at the BASF stretched a fiber like this by mounting rotors here, or a pair of rollers here. He noted that the velocity at one position away from the stagnation point has to be constant. The velocity, if you go back to the kinematics, the velocity is given, the velocity in x direction is equal to the extension rate times x. So here the velocity would be the extension rate times L0. And if you keep that constant, you're stretching your fiber at a constant extension rate. And it's so simple because your reference length, in this case, this distance, is kept constant. And then you can use and apply, if your reference length is constant, then the velocity, or the length change per time, is also to be constant to achieve a constant extension rate. So that was an easy way of getting, I mean, it was a possibility to overcome the problem of the drive. It still was a very difficult experiment. But Meissner got very nice data, and I will discuss some of his data when looking at extensional behavior when discussing material functions in extension. So far, the kinematics. I want to specify the type of experiments which we are going to look at to characterize the material in flow. We will only look at shear, and only look at extension, those two types of special kinematics. Let's start with the material behavior, behavior of polymeric materials in shear flow. The most simple experiment which you could imagine would be just the shearing of a cube. A cube is exposed to a finite shear strain, which is given here by angle alpha. So gamma is just tangent of alpha. And you would measure the resulting stress on an x phase, y phase, and z phase. You would have those 3 tractions. And with that, with those tractions, you will find, if the material is a piece of rubber, that the shear stress is proportional to the shear strain, and the coefficient of proportionality is the modulus, the so-called shear modulus. Now, in addition to the shear stress, there are also the 2 normal stress differences. This is the first normal stress difference. Remember, in shear flow, we are looking for 3 material functions which we have to identify. This is now the second material function. And in small deformations, that material function is given by the same modulus, the same shear modulus, times the square of the rate the square of the strain which we are putting in. And the third material function here would be given here would be observed for the second normal stress difference, tau yy minus tau zz. This is the difference between the y direction and the neutral direction here. And frankly, I don't know what, I don't have good data for that. It's probably hard to measure, and my friends who know much more about rubber haven't told me about what data I should be using. It's hard to get information on the second normal stress difference because it's just harder to measure in a clear fashion. Now let's move to a polymeric liquid. That was just a piece of rubber where the material behavior was just given by one material function, the modulus. And we know that from the Hookean behavior. The shear modulus is then related to the extension modulus, but just one property as long as the density is constant. Let's perform the same experiment now with a viscoelastic liquid where the overall behavior is liquid-like. It's not a solid behavior. And there we would again have a shear stress given by the modulus of this material times the shear strain, but the modulus now is a time-dependent one. It's a so-called relaxation modulus of the material. And the first normal stress difference is given also by the same modulus times the square of the strain we are putting in there. So this is the relaxation modulus. And there's the second normal stress difference, and I don't have enough data. I don't know what the behavior is in step strain and can maybe do some predictions. We can measure the second normal stress difference in a startup of shear flow or in the other conditions. But here for this little material element, for this simple looking experiment, we are already running into difficulties in measuring that. Okay, so what is this relaxation modulus? You know, one function defined the shear stress and the first normal stress difference. And this function would be good to know because then we can describe the behavior of polymeric liquids in small deformations. And here I sketched the time dependence of that function for you. It's the relaxation modulus. For the ideal Hookean solid, this would be given just as a constant value. The modulus would maintain its initial value, would not change in time. Time is here our independent variable. Now, for a viscoelastic solid, a solid which has some relaxation processes going on, you will have a large stress initially when deforming this material, but this stress decays in time until it reaches an equilibrium value. This is the so-called equilibrium modulus of the solid material, and that would be an interesting material parameter to know. But this parameter is not enough to describe the material behavior of the solid. You need also the transient behavior at short times, and that transient behavior would be given by a relaxation time spectrum of this material. Let me jump now to the other extreme at in the case of very small molecules, low molecular weight, the fluid behavior would be described by the Newtonian liquid equation. It's the ideal liquid behavior. And in an ideal liquid, the stress would be very high as long as you deform the material. But as soon as you stop the flow, it would relax very quickly. And I put a little tail in here. The relaxation time might be maybe 10 to the 9 or 10 to the 12, 10 to the minus 9 or 10 to the minus 12, something in that range, seconds. Very, very short relaxation times. So the stress would go down to 0 as you stop the flow immediately. But polymeric liquids have long time constants, and the stress which you build up when deforming the material will relax gradually in some function in time. And when it's down to 0 here, we would say the material is relaxed completely. The coils which were aligned during the deformation recovered their equilibrium conformation. And this behavior then is given by a spectrum of relaxation times because the material has to rearrange on long scale, intermediate scales, and we will have to identify that. We will discuss quite a bit about the relaxation time spectrum. Now, between the liquid and the solid is a material which has an ideal behavior. It's a so-called critical gel. It has a relaxation time which diverges to infinity. So it's like a viscoelastic liquid which has a leading relaxation time which goes to infinity. Or it's like a viscoelastic solid which has an equilibrium modulus which is still 0. So it's a limiting case for both those behaviors, and we have to specify this in experiments also. Now, for polymeric liquids, the modulus has been measured extensively. And I want to show the famous experiments of Ainaga, Osaki, and co-workers in 1971. So they deformed their material. Actually, they, if I'm informed correctly, they did it by hand. They didn't have a motor to do it, so they just deformed the material very rapidly by hand and measured the resulting stress. And since the deformation rate would be very high and the experiment would be over quickly, or the induction of the stress would be over very quickly, and then they just hold the geometry and measure at constant geometry. And what they find is that the stress decays like this. This is now in a log-log scale, the log of the relaxation modulus versus log time. They increased the amplitude. Here they performed that step strain experiment at larger and larger strains, and you can see that the time function is about the same. In fact, they shifted all those curves onto this curve, and you can see they all have the same shape, those curves. Except for the short time behavior, that's dominated by the glass transition, by the glassy modes of the molecules, and they are governed by some different rules, which I'm not going to discuss here. So the behavior of the entanglements and the flow of the relaxation at long times is independent of the strain, in the sense that it has the same time spectrum. But somehow at large strains, the modulus is lower, is decreased. That's a so-called shear thinning phenomenon. We are reducing the modulus, or we are increasing the molecular mobility, but all relaxation times are reduced by the same factor. And this phenomenon can be expressed in form of a factorized relaxation modulus. This would be the relaxation modulus at small strain. And this is multiplied by a function, a strain function, which is 1 at small strains, and it's smaller than 1 at large deformations. And the factorized function of strain function with another factor here, the time function, gives the relaxation modulus at large strains. And this type of formalism had a great influence on the formulation of molecular dynamics and the molecular models of Doi and Edwards, for instance, which write a physical model which has this property of factorization in step strain. So the material functions which we observe in simple experiments give guidance to the formulation of constitutive equations. And they will be used for checking the predictions which come out of constitutive equations also. So we will come back to those constitutive, to those material functions at times. The kinematics used in those shear experiments can be variable. We can have all kinds of time-dependent experiments performed. We can have a steady shear rate, or we can have oscillation or step strain put in. So we can have shear deformations of all kinds of time dependence and measure material functions accordingly. One of the most popular experiments to characterize the material behavior is the oscillatory shear. The material is put between two plates. This could, in this case, they are rotating with respect to each other, but you could also have two sandwich with relative motion of two surfaces. The important thing is that a strain is imposed on the material, which always goes back to 0, and then it goes back to goes negative, and then comes back to 0, and again back to 0. So the overall deformation of the material is very small, but still we are deforming the material versus during the cycle time, and we are observing now relaxation phenomena on the length scale, which corresponds to the time scale of the cycle. If we have a long cycle time, if we measure low frequency, we observe relaxation phenomena on large scale. If we choose a high frequency, we choose a short time, and we're looking at short, small scale rearrangements of the molecule. With that technique, we reach steady state very quickly. The startup time, when starting this an oscillatory shear experiment, we're reaching a steady response. Very quickly, after about maybe 1 or 2 cycles, we are in steady state, even if the relaxation times of the material are much longer. So it's a spectroscopic technique which allows to pick relaxation phenomena from the overall spectrum by just choosing higher or lower frequencies. Now that's used now in the following way: imposing oscillatory shear and measuring the stress response gives us an in-phase part of the stress, the stress which goes in with a sine function in time, and an out-of-phase part which goes with a cosine in time. Turns out that a Hookean solid in that type of experiment would have G double prime equal to 0, would only have G prime, and G prime would be a constant. And that would be the modulus of the Hookean material, the shear modulus. That's why G prime is called the storage modulus. It's connected with the elastic behavior of the material. A Newtonian liquid, however, would have G prime equals 0, would only have a cosine contribution, and G double prime would be proportional to a constant times the frequency. So, and it would be actually the viscosity times the frequency that would give us the G double prime. And that's why G double prime is called the loss modulus, because of the lossy behavior of the Newtonian material. Now, for viscoelastic materials, the behavior is in between, and in fact, G prime, G double prime are coupled with the so-called Kramers-Kronig relation, and we will use both of them to determine the spectrum of the material. So we should look at both functions for interesting materials. And here I have a typical fingerprint of a polymer melt. The frequency down here is shown, and then we have G prime, G double prime. At very low frequency, we allow the molecule to rearrange. We are basically probing the flow behavior of the material. So this has a slope of 2, and this has a slope of 1. We would have to I would have to derive that for you, but this is a typical liquid behavior. And then we have the so-called entanglement behavior, at intermediate time scale, the rubbery behavior of the polymer melt. And then at very high frequencies here, the material goes over to the glass behavior. This is a glass transition, and up here is the glassy behavior of the material. Let me demonstrate this with a bouncing putty. And remember, we had looked at the bouncing putty before and found that it flows over long times, and in fact it's hard for me to get it out of the cavity here. It was sitting on the shelf and was flowing. It was adopting the shape of the cavity it is on. The typical liquid behavior, see, it was just adopting the surface shape. A rubber ball would not do that. So it's really a liquid behavior, and at long times it is like a liquid. And this is the behavior down here. If I have the plot here, this is at very low frequency, the behavior. If you please, yes, show this. It's the behavior down here. If I deform the material with a steady load very slowly. Now I will demonstrate the behavior over here, the so-called rubber plateau. And the elastic behavior, I have to get up for that and try to make a rubber ball out of this. And you can remember that when deforming the material, here it's when throwing it like this, it's not perfectly round, so it's a little bit like it's very appropriate. It's like an American football, which would jump in all directions. But it is a rubbery behavior at that time scale, at the impulse load we are putting on this material. And now I want to go to the higher frequency behavior, to the glassy behavior. And for doing that, I will deform this material even faster than during the impulse, which I just demonstrated to you. And since I'm very strong, I can do this. So I'm deforming this, and if you maybe focus the camera on the face here, can you magnify this even further? Go. I didn't warn our projectionist here. When you look at the surface, it breaks like glass, the material. At very high rate of deformation, the material cannot relax during that deformation. And since the strain was very large, which I put in, it fractured like glass. So the melt behavior is really covering all those phenomena which we can see here in the dynamic mechanical experiment, the glassy behavior, the rubber plateau, and the flow behavior down there. Shall we break? Okay. Want to go to? Chemical Engineering, Polymer Science 757, Polymer Rheology, Professor H.H. Winter, Lecture 6B. We continue with the material functions in steady shear flow. And steady shear flow is defined by a constant rate of shearing. Gamma dot is constant in time. And the direction of shearing is also constant. It doesn't have to be a homogeneous shear flow. The shear rate might be a function of space, but it certainly has to be constant in time. So the shear stress is constant in time. The shear rate is not changing in time, and the result of that would be the viscosity as a ratio of that shear stress and shear rate, and that's the so-called steady shear viscosity, the only material parameter which we need to describe the shear stress in this type of flow. Now, what type of experiments would we be looking at? We would look at startup of shear flow. We would impose a shear rate, for instance, go from 0 to a finite rate, and observe the stress response. It goes through some maximum in many cases. And then levels often stays constant, and from here on, we would have a constant shear flow. And this could be verified, for instance, in flow through a pipe, where we would have a velocity field which doesn't change in flow direction anymore. And after some time downstream, the stress is fully established, and you would have steady shear flow. A way of checking that is birefringence. You can use a transparent pipe and look at the birefringence, and when that doesn't change downstream anymore, then you know your stress is fully established, and the steady shear flow is reached. Now, the result of the startup experiment is a function of the rate at which we do that. Typically, when we prescribe a shear rate going from 0 to a finite value and staying constant for our steady shear experiment, then the stress response at low rate would be a gradual growth of the stress. And if we divide the stress with the shear rate, then we would have a time-dependent shear viscosity. If we perform that experiment at very high rates, then the viscosity first grows the same way as before, but then it somehow goes to a maximum and levels off, and that's the so-called shear thinning phenomenon. The viscosity at high rates is much lower than at low rates. The startup time is also very different. The startup time here for the low-rate experiment, the so-called linear viscoelastic experiment, is equal to about the longest relaxation time of the system, or we could use that to characterize the longest, to define the longest relaxation time. And that's, I wrote down here, this is a criterion. The time bigger than lambda max will give us the steady shear flow, and the Deborah number would be defined in this fashion. However, at high shear rates, the reaching of the fully developed stress depends on a characteristic strain. Whenever the shear strain is applied to the material, say 20 shear units for a polyethylene melt, then the stress does not change anymore. Steady shear flow conditions are reached, even if the time is very, very short, even if the time is much shorter than the longest relaxation time. Somehow at high rates of deformation, you are eliminating some of the longest relaxation times from the spectrum in some fashion. So the whole spectrum is reduced to shorter times, and the startup time is also changed. So we would have now a new definition of the Deborah number, saying we have transient behavior at times which correspond to a strain which is smaller than the characteristic strain, and we would formulate that now with a strain here in this fashion. So that's quite an interesting variation on the Deborah number. Our parameter then is the viscosity, steady shear viscosity. Our material property is the shear viscosity, and it depends on the shear rate, which is given by an invariant of the rate of deformation tensor. And it doesn't depend on history, because our material element only remembers the same type of shear flow. All the history is defined by this rate of deformation tensor. So there's no new parameter introduced. It's a so-called constant strain history kinematics. So the instantaneous shear rate describes everything, including the history. Temperature would be parameter, and pressure. Pressure has very little influence on the viscosity, and I will not talk about this in great detail. Also, I don't have good data. It's very hard to measure behavior at very high pressures. And one objective for us in the future, I think, will be rheology at high pressure. And Paul, for instance, will look at that. That's a very interesting problem. Now, temperature effects are very severe, so we will talk about that, and combine the two. And this is really the next subject here. So if we say measure viscosities at different temperatures, viscosity curves as a function of shear rate. We perform shear experiments at different rates. And then we do this at temperature T1, at temperature T2, and temperature T3 at isothermal conditions in each case, but over a wide range of shear rates. Then we can shift our results, and I took some data from the literature. I have some nice graph here. This is taken from Meissner, publication in 1971 when he was at the BASF, the same Meissner who did the pioneering experiments in extension of flow. And he plotted the viscosity as a function of the shear rate at a set of different temperatures. And note that all of those curves have the same shape. And we can, in fact, shift those curves into each other under 45 degrees. 45 degrees here. We're shifting them, and we can shift them into each other. From an experimental point of view, that's quite an opportunity, because our rheometer will most likely have just a window, maybe a frequency window or a shear rate window as such. So we only would get data in this fashion. But now if we have data at different temperatures, we can shift them out of this window And our overall experimental window is extended by this so-called time-temperature superposition. So two things. We observe that the shape is the same for all those curves, which is remarkable. This is quite an amazing physical behavior of polymeric melts. And we use it as an opportunity in rheometry, and we'll talk about this later. So we can use the viscosity function at the measured temperature T1, and then we multiply it with some shifting. This gives us the amount of shifting under 45 degrees, and then we get the new viscosity curve at the desired temperature level. Or we could plot all the results in terms of just one viscosity function, where we divide the viscosity by the shifting and multiply the shear rate with the shifting. And the log-log scale, this is equivalent to the shifting under 45 degrees. And we note that just one shape of this curve is found. The characteristics of that shape now is the following. The viscosity at very low rates is leveling off, and the value is called zero shear viscosity. That's a very important material parameter for our melt. At higher shear rates, at shear rates beyond some characteristic rate, the viscosity will drop, and it goes down like this, and often is described by some Power-Law behavior as such, and that's so-called shear thinning behavior. So the characteristic shear rate gives us the transition. That's another characteristic parameter which we should be looking at. The slope over here is the Power-Law exponent, and then the temperature shift factor should also be identified in some experiments, and we have to talk about this. The characteristic shear rate now is the reciprocal of the longest relaxation time about to some very close approximation. So now we have the amazing fact that a steady shear experiment can be used to determine the longest relaxation time of the polymeric material. And the reason for that is basically the steady state condition. When you shear the material in steady state, you build up stress as fast as you're relaxing the stress. So under those conditions, your material only memorizes a finite part of the strain history, and that's expressed then in the stress. We have to come back to this when talking about linear viscoelasticity. So for the de Boer number, we have a new definition. We talked about that already. The viscosity is not the only material function. I just plotted here the viscosity as a function of shear rate. The first normal stress difference is described by a material function. This is the coefficient of the first normal stress difference. It's also shear rate dependent. And then there's the coefficient of the second normal stress difference, which I don't have data on here. It's about 10 or 20% of this function, and it's negative in sign. In Utah, Christiansen and now Magda are measuring the second normal stress difference very nicely. It's an experiment which is somewhat harder to do. The viscometric functions, that's the three functions which describe the material behavior in shear flow, depend on molecular weight. The shear viscosity, in this case, I plotted the behavior at very low rates. This zero shear viscosity is a function of molecular weight and goes with a 3.4 power at high molecular weights, or it goes with with the first power here at very low molecular weights. Yeah, with the first power. And the first normal stress difference has a coefficient which goes with the 7th power of molecular weight. That's a very strong dependence of molecular weight. Very often, the intrinsic viscosity is used to check the molecular weight of some newly synthesized polymeric material. Now, the intrinsic viscosity only goes with the 0.6 to the first power of molecular weight. It's a very weak function of molecular weight. And preferably, one really should use the zero shear viscosity to identify changes in molecular weight. It's much easier to do. So, but conventionally, some people are just used to the zero shear, to the intrinsic viscosity to test their material. So note the sensitivity of the material functions in shear to small changes in molecular weight. Now, that type of sensitivity you see throughout rheology. That's one reason why processing is so sensitive to small changes in molecular weight. Or that's why mechanical properties of polymeric materials change over such wide ranges when you change only small parts of the molecular architecture. So this is just an expression of that sensitivity. Now, the Power-Law behavior, the representation of that function. Let me go back to this. We want to describe this function now with some simple mathematical format. We want to represent this viscosity as a function of shear rate and then use it in mathematical calculations. The most simple thing would be just a straight line here, neglecting the zero shear behavior, just a straight line here. And that's the so-called Power-Law relation between stress and shear rate. And the two coefficient is the front factor, and the exponent is between 0.2 and 0.6 for conventional polymeric materials. Now, this function clearly fails at low rates. So people truncate the function here, and they say at low rates, it's just given by a constant value, including temperature dependency in this formulation. And at high rates, it's described by a Power-Law like this. Now, this truncated Power-Law can be represented in a sigmoidal function, 1 plus a Power-Law, and at low shear rates, this function would reduce to 1, and then the viscosity is equal to the zero shear viscosity, and we recover this upper part of this function. And at very high shear rates, gamma dot, now, this function here, this part here, dominates 1, so this 1 can be eliminated, and this function here is really approximated by this Power-Law. So Corot's type of Power-Law captures both parts, and it really gives a fairly good description of the viscosity. Can be used nicely in numerical calculations. Analytical solutions cannot be achieved anymore. Analytical solutions really achieved very nicely with that function, and the results are, quite a number of predictions are permitted by just doing that. Now, it's also very popular to use this viscosity, this shear rate dependent viscosity, and enter that into Newton's law of viscosity, where you take the shear stress is proportional to the rate of deformation tensor times the viscosity. And the viscosity then would be a function of the second invariant of the rate of deformation tensor. And then you could, technically, you could calculate the stress in extensional flow, or you could calculate normal stresses in addition to shear stresses in shear flows. This has been discussed extensively in Bird, Armstrong, and Hasaga. Here there's a whole chapter devoted to this so-called generalized Newtonian liquid. Now, let me express a warning here. This viscosity function is only good to describe the shear stress in steady shear flow, and it's not good for calculating normal stresses or for calculating extensional flow. Technically, it's okay to use that. You're not violating continuum mechanics, but practically, your calculated results are nuisance, are physically meaningless, because remember, we are just using the behavior as which comes from steady shear flow. So we should keep that in mind. So I would like to compare the two viscosities would like to compare, this is, actually I didn't even bring that. I will bring that next time for you. This is the viscosity defined for a polymeric liquid, and this viscosity depends on molecular weight to the 3.4 power, and the viscosity of a Newtonian liquid is linear with molecular weight. The polymeric liquid during startup shows a delay in reaching steady shear flow conditions, while the Newtonian liquid instantaneously reaches steady shear conditions. Only inertial effects would hinder you from reaching steady state immediately. Now, for the polymeric liquid, the viscosity describes the relation between shear stress and shear rate in steady shear flow. And only that relation is being described. While for Newtonian liquid, the viscosity describes the relation between the stress and the rate of deformation tensor. And this is a tensorial equation which you can use to describe shear flow, extensional flow, any flow. You can describe any complex flows with that. And this viscosity is shear rate dependent, while the viscosity here is independent of the shear rate. So it's very, very different, but we both of them we call viscosity. So you have to be aware of those differences. The viscosity function can be used now to calculate flows, to calculate, for instance, shear thinning. And, when we talked about phenomena in polymeric materials, I mentioned this phenomenon of shear thinning, where we would observe a liquid being pushed through a pipe. This would be the velocity distribution. And we would measure the pressure drop, which is needed to achieve this flow. Now, this pressure drop is a function of the average velocity in the system. For Newtonian liquid, it increases linearly, and for the shear thinning liquid, it somehow is deviating. The pressure drop is lower than one would predict from the zero shear viscosity. And we would like to model this now with the material function, which we would measure, which we just discussed before. And we would look for, in our solution, we would look for the stress distribution in pipe flow, the shear stress as a function of the radius, velocity distribution, and also the distribution of shear rates as a function of the radius. The flow is described by the following. We would use the velocity gradient in radial direction. That's the shear rate. That's the parameter. The flow is one-dimensional. There's no change in flow direction, or no change in circumferential direction. By one-dimensional, I mean that we neglect end effects, inlet and outlet effects. We really have fully established shear flow when analyzing this here. So end effects are neglected, and we are looking at very low Reynolds number flow at laminar flow conditions. So how would you model this type of flow? You would take a book, for instance, like Bird, Armstrong, and Hassager here, and then you would go in the back, in the table, and you would look at the stress components in cylindrical coordinates. You would immediately go to the component version, and you would reduce these components now by neglecting all acceleration, all inertial terms would be equal to 0 compared to the viscous terms. You would neglect gravity. This is not used in this case. So this would be the component in flow direction. This is the component in radial direction. And this is the component in theta direction, which really doesn't give any contribution. We're assuming rotational symmetry in this case. So this is our momentum balance. And we would analyze the equations now term by term. The component in flow direction contains the gradient of the shear stress multiplied with R and taking the derivative here, and this is given here with a pressure gradient in x direction. And the R component here is giving us the normal stress difference between the 2 direction and the 3. This must be between the 1 direction and the 2 direction. So I have to check that. I think this should be the first normal stress difference which we are getting here. Now, the pressure gradient is not a function of the radius, and it's not a function of theta. So if this is not a function of the radius, we can treat it as a constant when integrating this function, integrating with respect to r. And then we are eliminating one of the r's, and the integration constant is equal to 0 to satisfy the symmetry condition at the center line of our pipe. So this would be the shear stress distribution. The shear stress increases linearly with the radius. Yeah, this is a constant linearly with the radius, and the pressure gradient is really negative because the pressure decreases in flow direction. So so the shear stress is negative. And we can combine now this equation for the shear stress, which we just calculated, with the material function, where we would say the shear stress is given by the local shear rate multiplied with the local viscosity. And the viscosity locally depends on the shear rate. In this case, the shear rate is not constant. We have to introduce now the function for the shear rate, which captures the shear thinning phenomenon, the shear rate dependence. And I did this by just describing it with a power law. Yeah, the viscosity is given by a power law. Now, this power law is determined in the following fashion. We would take the viscosity function, say this is a viscosity plot somebody gives you, and says, why don't you calculate the pressure drop in pipe flow for me? So how would you determine the power law in this case? You would take a certain viscosity here. Let me just draw that, because there's a very simple way of determining the parameter of the power law. You would choose a shear rate, say gamma dot super 0, and then you would read the viscosity which is occurring at that shear rate. See, remember, you have the data. Somebody gives you the data. So you have now the viscosity super 0. So these are associated with 1 point on this curve. And then you draw the slope here on this curve, and that slope is equal to n minus 1. You know, n is smaller than 1. It's a negative slope. So you're getting the slope directly from this plot. And you have everything to introduce into your equation. You have the viscosity we pick 1 point on the viscosity curve. You have the shear rate at this point. And then this is the shear rate dependence. And you enter this up here. Okay. The next problem to overcome is the following. The viscosity is shear rate dependent in a fashion where it doesn't matter whether you shear in positive direction or negative direction. It's basically the absolute value of the shear rate which determines the value of your viscosity. So we have to enter the absolute value here. The shear rate is given by the velocity gradient in our case. And we know that the velocity gradient is negative. Where is my plot for the shear rate here? Here, this is the shear rate This is the velocity gradient. Velocity decays in radial direction, so velocity gradient is negative. The shear rate is negative. So to overcome the absolute value sign in this equation, we would have to replace this by minus the value. So minus the shear rate is a function which is positive. Okay? So this is a positive function which we are entering here. And we rearrange everything, then you get the pressure gradient times R over 2 given by the shear stress, and the shear stress is given by the viscosity times the shear rate. And you can integrate this now. You have to integrate it actually twice. And no, you integrate it. We already integrated once to get the shear stress. You integrate one more time, and you find the velocity distribution as a parabola with a front factor like this. This is the average velocity. In this case, the average velocity depends on the pressure gradient. This expression in the bracket is positive. Remember that the pressure is decaying in flow direction, so the pressure gradient is negative, and this is a positive function. So we have a solution for the velocity field in pipe flow. This would be a summing this up here for pipe flow. We have the velocity distribution, which is now more flat. It's a parabola, which is somewhat more flat than the parabola of second order for the Newtonian liquid. And we get this by introducing the shear thinning viscosity into our equation. The shear rate was defined by the velocity gradient. The shear stress was given from the momentum balance and was also given from our material function, the behavior in steady shear flow. We are combining this to eliminate the shear stress, and we integrate to obtain the velocity, get the average velocity, the volume flow rate, the shear rate, everything. And then now we can come back to the original equation here, or to the original experiment. We could plot the flow rate versus the pressure gradient, and you can see now for the power law, we would have a zero slope here, this type of prediction. The prediction is wrong at low rates because the power law doesn't describe the behavior at low rates. It would give us an infinitely large viscosity at low rates. So there are deviations. But processing occurs at very high rates, and the predictions are very good. So that's where it's used, and that's where it's used very successfully. Now, with this equation, we can calculate not only the details here, volume flow rate, we can calculate the shear rate distribution in the system, we can calculate residence times, shear strain. All the details, all the insight in pipe flow can be achieved from a simple power law solution. From that simple material function, we only need the shear stress to describe the stress in this situation, to have a complete description of everything. We could repeat the same calculation for slit flow, and you would get a set of equations like this. That would be a very nice exercise for you to do, actually. Then you see how you determine the shear rate, in cases where it's negative, get rid of the absolute value signs, and go through the details. That would be a worthwhile exercise. So that's all I want to present about steady shear flow. I hope you got an impression about the amount of information which is included in the steady shear viscosity. And the steady shear viscosity is so important because shear flows occur in many, many processing operations. So we are able to use that one material function to make predictions in many applications. Next time I will continue on material functions. So thank you for today. That's it.